data age. Now data become more and more important in our daily life. Some of you probably have the same question as me, like, what is the temporal data structure? And I think you will find out the answer in the next talk. Let's welcome our second lecturer, Josie Leingang.
Good morning. Thank you for joining me for my first conference talk, Temporal Data Structures with SQLAlchemy and Postgres, a real mouthful. My name is Joey Leingang, and I am an engineering manager at Clover Health. We are a San Francisco, New Jersey-based, two different places, based health insurance startup. And we use Python and Postgres to build operational and clinical software. It's excellent for me because I've been a Python programmer for quite some time now. I'm not a particularly interesting person on Twitter, so I encourage you to check out our technology blog rather than trying to follow me on Twitter. You won't actually get any good content. So, briefly, our agenda today. We're going to take a look at what temporal means and why you might want to use temporal data structures. I'm going to briefly go over some of the things we explored at Clover Health, and then get into the fun stuff with Postgres and SQLAlchemy. This is a fairly technical talk with a good bit of code, and I will hopefully have some time at the end for some questions, and hopefully you will have learned something new. So, time. It's like a big ball of wibbly-wobbly, timey-wimey stuff. That's great, but if you tell that to someone who is using your software, or gasp, an auditor, they're probably not going to care for your sense of humor. At Clover Health, our applications need to have a rich and consistent history. We need to be able to answer questions about when things changed or why they changed. And compliance and auditing certainly matter, but you want your software to be a joy for your users to use. You want it to be forgiving, but not forgetful. And if you were in the talk prior to this, you've maybe experienced a lot of date times, and a presentation about applying date times to absolutely everything in your application might be a little bit scary. Don't worry, it absolutely scares me. So this is the dream. Every time you've added a date created or date modified to one of your models, you might ask yourself, wouldn't it be nice if you could actually know all of the times that it was modified, or what changed when those modifications happened? We're going to be looking at a simple example today with friends and where they live, some real Big Brother stuff. I want to know where all of my friends live now, but everybody seems to move around. So I don't want to forget where they've been. In this example, Rachel, someone I met in New York, and then at some point in the future, she moved to San Francisco. Let's see how we can actually pull this off. First thing we looked at Clover was just using a log file. It's a time-honored activity, and let's be honest, we all log everything, right? So everything that occurs generates an event, you get a nice timestamp, goes into a file or a database somewhere. You can even beef that up if you wanted to add structured logging. Maybe you're using JSON to give you a little bit more information about what happened. And this definitely works for auditing purposes. It's a little bit harder to build application features with. And so we decided we'll keep logging things because logging is the right thing to do, but we're going to need something a little bit different. The next thing that we looked at was version tables. This is another very common way to keep history. You start with two tables. One is the current state of the world. So here we've got that friend table and some entries in it and where they currently live. And then you have a history table. That history table has basically the exact same shape, but it has some sort of history bookkeeping, shown here as a timestamp. You could collapse this into a single table where the primary key is the ID of your friend and the version of it, or the timestamp of it. And this definitely works for auditing, makes it a little bit easier to build features on top of, but it's still kind of hard to ask the question, what specifically changed, and how long was a particular person in one location? So the thing that we actually settled on is per property tracking. This is the last thing we tried, and we found it to be very powerful. So you still have that current state table. All of my friends are listed there and their current location, and that drives the vast majority of our read operations. But now we've split out history into two streams to keep track of. And the first thing is that friends clock table. It has a foreign key to the friend, a tick, which is an integer that tells us each time an edit happened, and a timestamp for when that occurred. And then we pull that property out into a separate table, the location history table. And this lets us know where a person was at any point in time. All right, so let's actually make this happen. We're going to create some tables in SQL first. And the first table we're going to make is that current state, the friend table. We give it a primary key because we always give everything a primary key. And we add a name and a location as simple text fields. We're going to add that column vclock or version clock, which is an integer. That's going to keep track of every generation of edit. The second table that we create is that clock table. It has a foreign key to our friends, a tick, which is an integer once again, and the timestamp. Don't forget your time zones. Every time we change a friend's location, we're going to increment the version clock on the friend table and create an entry in our clock. So, slight diversion, we got to talk about ranges. Ranges are an awesome thing in Postgres. And there are two types of ranges that you can consider. There are ones that have discrete values and continuous values. All ranges have an upper and a lower bound regardless of the type. Integers and date ranges are discrete. Think of 1, 2, 3, 4, and so on, or May 20th, 21st, 22nd, and so on. Numeric, or floating point, and date time are continuous. Date time actually has a fixed precision because that's how time is kept. But for your applications, you can consider date time ranges to be continuous. Ranges not only store the upper and lower bound in a single column, they give you some special operators. So what we have here is some examples for creating ranges and doing operators on them. The first one, which is most important for this talk, is containment. We can ask the question, is the number 3 in this range of 10 to 20? That answer is no, it's not. We can also do things like check if the ranges overlap. In this situation, those ranges do overlap. We can ask, what's the upper or lower bound in a range if we need to pull that value out distinctly? There's also intersections. You can ask if ranges are empty. There's a whole set of operators on ranges, and the Postgres documentation is really excellent. That's where I would start. So the next thing, we need to set up some criteria. So we're going to add a little bit of exclusion, and it's the only good kind of exclusion. We need a special Postgres extension, btree_gist. GIST stands for generalized search trees. They let you make arbitrary indices over multiple columns with a bunch of different operator classes. And so our location history table is going to take advantage of this. We're going to give it an ID, that primary key, because once again, everything gets a primary key. And we're going to have a foreign key back to the friend that we're keeping the location history on. And the version clock is now a range rather than just being a single entry. The actual location value at that point in time, and this new thing, which is an exclusion constraint. And this exclusion constraint says, for any friend that we have, they can't have an overlapping version clock. What this means is a person can't live in more than one location at the same time. So Postgres is going to keep track of that for us. What does this look like if we actually try to create some history entries? So We're going to create a history entry for my first friend, Dave, who lived in Tucson when I met him, or version 1. Tell Postgres to insert it, no problem. Time passes, Dave moves to San Francisco, a good choice in my opinion. We're going to create the next entry. So same friend ID, now in San Francisco, and we're going to say version 2 and up. Postgres says, slow down there, buddy. You can't do that. There's overlapping vclocks. So to actually make this work, we need to update that previous entry that we had before we insert the new one. We would do this all in one transaction so that we could keep a transaction time on it. Creating a lot of tables, writing inserts and updates is very tedious. And this is PyCon after all, so I had better show you some Python. First thing we're going to need is a whole bunch of inserts. I don't really want to talk about them. I like SQLAlchemy as SA, but that's a contested thing, so we'll skip right over that. And SQLAlchemy declarative. This is a tool in SQLAlchemy that allows us to think about our software in terms of classes, and we can apply object-oriented programming to our problems. So my friends, they have names, they have locations, and now both of them can change. And we're going to keep all of that in a separate schema in Postgres so that we don't get confused when we're looking at our tables. That model had a mixin on it, a special mixin called Temporal Model. Let's take a look at what that does. So this is a declarative interface to defining your history. It's got that column on it, vclock, which is an integer. And every model that we mix this in on gets it. Very typical do not repeat yourself stuff. And then we have 4 methods that call into core parts of the library. We've got this clock tick. We have a temporal map. We have an initializing of the clock. And we have a mapper class. And let's take a look at each one of these methods individually. So first up, SQLAlchemy declared attribute. This is a scalar-like property that can be called from the class directly. SQLAlchemy treats declared attributes as returning a special construct used when mapping a class. And we typically use this to mix in custom logic for foreign keys and relationships. But in this case, we need to override a core SQLAlchemy directive, which is the mapper class itself. It's the M in ORM. And we need this class to be mapped first, then we can set up our history tracking on it. So we build a function in line and we return that. SQLAlchemy will use that function to map our class. Next up is that temporal map function. And here, I'm going to do a bit of hand waving. The work is not actually done as comments, but it's a very long function, so we can't show the whole thing. First thing is, this is a Python static method. Means there's no implicit arguments to it whatsoever. And in fact, the second argument to it is class, CLS, which you normally see as the first argument. But because it's passed in when we're mapping, this is actually the mapped model that we want to generate some history for. So what it does is actually looks at all of those properties that we said we wanted to keep track of. It builds the history tables and the history models for it, builds that clock table and the clock model, and then it configures a whole bunch of relationships that go back to our friend model. You could probably swap out the underlying storage mechanism here. So if you wanted to do a log file or you wanted to do version tables, you could replace the logic here. The last thing that we do is we have to set up an event listener. So whenever you create a new friend or whenever you meet a new person and you want to make an entry, you have to start history somewhere. And this is another SQLAlchemy feature that allows you to listen to events when a model is created, or when an instance is created from that model. So what happens when we actually start keeping history? This is, once again, another static method, the init clock. And this is the thing that we just listened to. So we want to make sure that our versions start at somewhere sane. We'll start it at 1 unless you tell it to start at a different number. And we're going to generate that clock entry with the current timestamp. There's a new thing here that I haven't talked about yet. It's activity. Activity is a special feature in the temporal library that allows you to define a custom model to represent how or why something changed. So you basically give your history any context that you want. I'll let your imagination run wild on that. It's a very important feature at Clover Health. Finally, we have the most gnarly method in the library. This is the clock tick. This is what happens when we change something. We've made it a Python context manager so you can logically think of all of your changes corresponding to one edit. We come in, so you're going to say with some instance .clockTick, and that instance had to be selected from the database, so it already exists in a SQLAlchemy session. We're going to disable autoflush. Autoflush is usually a very good thing in SQLAlchemy that as it needs to read things from the database, it will automatically write your changes. It allows the session to stay in sync. But we got to be very careful about writing all of our things at the same time. So we're going to disable that. Then we yield to the business logic of our application where we make those changes. We come back in and we check, did anything actually change? If so, we will go ahead and increase that version clock by 1. We'll create a new clock tick entry, and we will associate the activity instance with it if necessary. And we add all of that to the session. And at some point later, you would do a flush or you would do a commit, and it would all get written to the database. So what I should say is that the model mixin is not the only way to use the library. It looks an awful lot like a Django meta class, which is intentional. But there's another way that you could use it. We have a decorator in there that you can just add a clock to anything. You give it a list of the properties that you want to track. Once again, activity class is totally optional. And you can specify the schema that you want to write all of this stuff into. Excuse me. So if we wanted to use the decorator on our friend model, it would look a bit like this. Just add the clock. We say, once again, let's keep track of a person's name and their location. And once again, let's store that in the history schema. So this was the dream that we had when we started the talk. Let's come back to it. We can kind of see how it all works together now. I met Rachel in New York. Some time passed. She moved to San Francisco. So I update her record with a clock tick. I save it to the database. And now I can actually inspect the history of the location. The first entry was New York. The second and current value is San Francisco. It's very cool. Each property is actually tracked independently. So, what are the takeaways? Keeping history on your models. If you want temporal data structures, you are going to add a lot of complexity to your application. This method creates a ton of tables, right? And that's sometimes very scary. So I probably wouldn't use it for absolutely everything. You have to decide what method you need and what are the trade-offs there. Bulk operations with temporal, with log files, with version tables, all of them very challenging. You have to do a number of inserts, potentially a number of updates. So doing any history stuff in bulk is very confusing. You also have to decide what is the timeline that we want for this bulk operation. Are we doing things back in time? Do we need to forward date anything? It's very complicated. Postgres and SQLAlchemy, however, are very powerful. And together with the ranges and the exclusion constraints and that ORM, all of those features in there, you can kind of come up with a mix of history tracking that works for you. So this library actually is open source. You can check it out on GitHub. We don't have any documentation yet. The test coverage, however, is very good. So it's very good. You can use it, download it, try it out, add it to your models. There's the decorator, there's the temporal model mixin. It will get published to the Python package index as soon as we get some documentation. You should know that it does require some more up-to-date things, Python 3.3 or better, SQLAlchemy 1.0.15 or better. It only works with Postgres, and only Postgres 9.3 or better, and PsychoPG 2.6.2, which gives you those sort of underlying range type primitives. Now, I went way faster than I actually intended to. I'm out of content. Ready for questions. I'm supposed to ask you to use the microphones as well if you have some questions.
I was wondering, what about if you wanted to track rather the history of kind of sets of objects, or rather than the relationship between objects? So instead of tracking scalar properties on an individual object, so maybe you wanted to know like the history over time of like which of your friends are friends with other friends. So like, have you looked at that or tracking the history of the relationships between objects?
Yeah, so you actually can track relationships. I did not show that. It's a little bit more complicated of an exercise. Materializing those relationships is actually the hard part. Keeping track of them as you insert them into the database, where you use SQLAlchemy's ORM to keep track of that stuff, makes it a breeze. When you need to pull it out and you have to sort of decide, how do I display this to someone? Is it going to go into an audit log, or is it going to be in the application itself? You kind of have to make game time decisions. So that's why I didn't show it. But yeah, you can absolutely do that.
Thank you.
Thank you.
All right. So you showed, I think, very briefly on the screen what looked like a fancy Postgres feature, the gist.
Oh, yeah, yeah.
And
let's go back to
part
that.
of what this dream would be, I think, for me is after wide swath of people have had many updates over time, to go and ask, well, what was the situation as of certain day 2 years ago, certain moment? Does that query end up being well indexed here? How does that work?
Yeah, so with everything being indexed and with the exclusion constraint, there is an easy way to sort of say, give me the state of this model at a point in time.
The state of, sorry, of this one instance? Or
of one instance at a point in time. That's what we've built now. Once again, it kind of gets back to how do you want to materialize that data and how do you want to interact with it in your application. So we haven't quite decided, do you get the full class or you just get like a dictionary of the information at that point in time? Can you move forward and backwards from it? We haven't built any of that yet.
Cool, thanks.
I'm curious, did you have to deal with bitemporality? So in your example, for example, not only where somebody lived, but what their job was, and you want to know the full Cartesian product of where they lived and what job they had over time?
Yes, so the question's about bitemporality. So temporal is just time dimensions, and bitemporality is 2 time dimensions. This is very cool if you want to say, I knew something about this at this time, and the world knew it at a different time. So if you were to add or keep track of a timestamp property, you are actually making it bitemporal just by doing that. The other thing is, under the hood, the history tracking actually uses Postgres current transaction timestamp. So it does keep track of when did the system know about this stuff. And so if you need to differentiate when did the system know about it and when did I know about it, you can do that.
Hi. Postgres has a lot of really interesting advanced features that I don't know a great deal about. The range
feature is a new one to me. It looks like a nifty use case that you're using it for, but it also looks to me like this is basically just a sequence of integers one after another.
Yes.
Can you talk about the trade-offs of using the more complicated range versus just integers?
So the reason we use integers is it makes thinking about your data a bit easier. If you're looking at the current state table, you have an integer right there that tells you how many times did this change. So if I needed to manually construct queries to read the history entries, I know how many queries I'm going to have to do. You would usually collapse that into one if you really wanted to get fancy with it. But the fun thing with the ranges is when you stop thinking about just the discrete ones and you start thinking about the continuous ranges. So you could use the date time with time zone range, and that would keep track of a full continuous history. And you could actually build a thing where you slid the time forward and backwards, and it would know exactly where you are. You're absolutely right, though. The integers are just super easy to reason about, super easy to store and select. It doesn't use a ton of disk space. And I think you should always start with the easiest thing first. That's why we started with the integers. Thank you.
So on the subject of the easiest thing first, a very, very naive approach to this problem would be that you have a single table and you have a start time and an end time for each entry. And that has the advantage that when you're doing historical lookups, you can use between and you can get the entire state very cleanly. What advantages does your approach here have over such a naive solution?
So we looked at that. And the reason why we ultimately decided on this was there are some properties of our models at Clover Health that change very frequently. They're like high velocity changes. Other properties do not change that frequently, but we still need to keep track of it. For the ones that change very frequently, there's also auditing requirements related with that. So we needed to build features for those properties specifically. This allowed us to sort of think about everything as the history is always being kept, but here's a nice, easy interface for those high velocity changes, and you can use it for the low velocity stuff, but you probably don't even need to worry about it.
Got it. Thanks.
Hi. So one, you did give the warning about the bulk inserts as such. But still, the question is, if you have, say, 5 properties that you're going to track, you're going to be inserting into 5 different tables.
Oh, yeah.
So now you're wrapping that under one transaction. Now, how do you see that going? As in, isn't that a bit dangerous? As in, aren't you going to get a huge performance problem even for a single insert, forget bulk? And have you tried looking at Postgres' listen and notify to, abstract away from, as in putting the data into the history tables, away from the transaction, that is after the transaction happens?
We looked at doing that with triggers and stored procedures. I'm going to be completely honest with everybody. Yeah, it is very dangerous to have a whole rack of tables and have to do a whole bunch of inserts and updates. But living dangerously is very fun, so I encourage you to do it. What we've actually discovered, we've been using this library in production on sort of audited software for many months now. And the performance, though less than some other methods, or if you didn't have to keep track of history at all, it's definitely a little bit slower. It is not slow enough to actually cause a concern. And we actually do a tremendous amount of bulk operations with it, and the performance is totally fine. Postgres is awesome. It's plenty fast. You can beef it up. Don't worry about a lot of tables. Don't worry about a lot of inserts. Postgres has totally got your back.
Hey there. Just wondering your thoughts and if there were any considerations to having a single source of truth being that history table, as opposed to having the history table and then also having to update the user object, so you like get the last location in that history table for the user?
Yeah, that's a great question. So when we first started building this, we did have a dream that we wouldn't need that current state table at all, except for properties that are immutable. we're just about at time. So you could do that, but it does make the work on data science significantly harder because now they got to join everything,
ETL,
even to
yeah.
get the current state. Yeah. What's up? Last question.
Maybe I can come up after, but how do historical corrections work with this schema? If someone said they lived in a different city, but they actually didn't.
So that would be where you get into the realm of bitemporality so that you can rearrange history, but you're only ever moving forward with your inserts. The way we think about it at Clover is, if you've made a mistake, remember, the software is supposed to be forgiving, but not forgetful. You just update the record, and you create a new history entry, and you go forward in time. If you did need to have that different timeline, that would be where you would add the bitemporality to it.
Thanks.
All right. I think we're out of time. Thanks, everybody.